Welcome back to our video series on FWIME, and today we're still in part 1 entitled Theory and Design. So we previously saw how we constructed our objective function, and in this objective function we introduced two features, the data correcting term and the annihilating term. In the last video we explained how we computed our data correcting term, and in this video we're going to show you how to gradually reduce the contribution of this data correcting term while still ensuring phase matching between observed and predicted data. And indeed, this will be achieved by adding an annihilating term. So here again, we're going to make a design choice. Remember that the data correcting term is linear with respect to p tilde optimal. Therefore, if we make p tilde optimal vanish, then our data correcting term will also vanish. And the first obvious choice for our annihilator is to simply try to minimize the L2 norm of p tilde optimal. However, we have not been able to succeed with this strategy and we had to find something different. So instead, we decided to use a modified and invertible version of the differential semblance optimization, or DSO, operator, first proposed by Symes and Kern in 1994. This DSO operator has been successfully used in a wave equation-based migration velocity analysis technique referred to as WIME. This technique uses extended migrated images and is based on penalizing the defocusing of space lag common image gatherers while focusing the reflected energy at zero space lags by optimizing the velocity model. Additionally, it has been observed that the objective function associated with this technique tends to be smoother and more robust to the presence of local minima compared to the conventional FWI cost function. In FWIME, we wanted to leverage the benefits of this DSO operator as well as the smoother shape of the WIME objective function, while still diminishing the L2 norm of the optimal extended perturbation, p tilde optimal. For that, we slightly modified this operator to suit the specific needs of FWIME. So this is the outline of today's video. In the following, we're going to provide a brief overview on why and how we modified this DSO operator for FWIME. First, we explain how extended images are useful for MVA or WIME. Then we explain how the conventional DSO operator is a great tool to measure the unfocusing of the images. And finally, we show our modification and show how critical it is for the success of FWIME. Okay, let's begin with extended images. So we go back to the same Marmousi example we described in the previous video. Let's assume that we're given a starting model that we know is inaccurate. Let's call it M subscript bad. And for this model, we're going to compute p tilde optimal as if we were computing the first variable projection step, and we're going to use a horizontal subsurface offset extension. On the bottom left panel, we show a common image gather extracted at a horizontal position of x equals 13 km. And the vertical axis represents depth, and the horizontal axis shows the subsurface offset extension. On this common image gather, we can clearly see some events with what we call a frowning move-out, as shown by the green lines here. Moreover, this type of move-out usually indicates that the velocity model used to compute this image is too low. And now we're going to use a good model, which is a slightly smooth version of the true Marmousi 2 model, and we're going to compute the corresponding p tilde optimal with the variable projection step. And the right panel here shows the analogous common image gather extracted from this new p tilde optimal at x equals 13 km. And both panels are displayed with the same grayscale. Let's now rename both panels. On the left, we're going to call it p tilde optimal of M bad, and on the right, p tilde optimal of M good. And as expected, by comparing the two panels, we can see that the event corresponding to the same reflections in the data are mapped differently in the extended space. So on the left panel, the events are displaying a strong frowning move out with plenty of energy clustered away from the physical axis, whereas on the right panel, the energy is much more focused in the vicinity of the physical axis, as shown with the green arrows. And this illustrates the well-known fact that migrated images computed with accurate velocity models should have reflected energy more focused towards the physical axis. And now that we gained better insight on how should a migrated image look like in the extended domain when computed with an accurate velocity model, it is natural to think about designing an inversion strategy that would use this information contained within these images. In this inversion strategy, the input would be a similar image as p tilde optimal of m bad. And the goal of this method would be to update the velocity model, recompute p tilde opt at each time, and then stop when p tilde opt is as focused as p tilde opt of m good. And this technique indeed exists. It is referred to as WIMVA and belongs to the large family of migration velocity analysis, or MVA techniques. And now we're going to talk about how the DSO operator can be a very useful measure of the unfocusing of extended migrated images. As mentioned before, this property makes it adequate for MVA techniques. The goal of WIMVA is to find an accurate velocity model such that when we compute p tilde opt, it gradually forces the energy of the events located in the extended axis, here shown with the pink arrows, to slowly converge towards the physical axis, here shown in the green dashed line. And a natural way to measure the unfocusing of such images is an operator that applies to all the points in the image a penalty that only depends on the distance between the point of the image and the physical axis. And here we show the graph representing the conventional DSO penalty function applied to any given point in the extended image. And as expected, the penalty increases as a function of the distance between the point and the physical axis. So to further illustrate this conventional DSO penalty, or this DSO weight function, let us consider a point on the image shown on the left panel by the green triangle. To obtain its penalty value, we first compute its distance with respect to the physical axis, h of g. Then we simply compute its mapping on the DSO penalty function, and we obtain its weight, p of g. Now let's assume that I want to compute a penalty value for a point located on the physical axis of the extended image, here shown on the left panel by the pink dot. In that case, the conventional DSO function will assign a 0 penalty value, as we can see on the right graph. And to better visualize the effect of this conventional DSO operator, we apply it to every point on this common image gather. And the result is shown here on the right panel. Note that for visualization purposes, the two panels are displayed on different grayscale. On the right panel, the energy of the events located at far offset have been boosted, which was expected because they contribute more to the unfocusing of the image. And indeed, the near offset are less penalized, shown by the zone within the green box. And finally, the weight assigned to the physical axis is exactly 0, as shown here with the green dashed line. And now that we understand the idea behind the conventional DSO operator, we're going to see why we needed to modify it for FWIME. One key point to realize is that FWIME and WIMVA have slightly different goals. On one hand, WIMVA tries to adjust the velocity model until the extended migrated images are well focused, and the output of WIMVA is not only a final and hopefully accurate velocity model, but also its corresponding migrated image. However, in FWIME, we said that we are not really interested in the extended optimal perturbation, or p tilde opt per se, and that it was just a tool to help the inversion converge to the global minimum. So we know that for MVA or WIMVA, the ideal image, i.e. the image computed with the most accurate velocity model, is indeed a well-focused image. But in FWIME, how does our p tilde optimal look like when we compute it with a true velocity model? So now to answer this question, we need to go back to the original definition of p tilde optimal. And here we evaluate p tilde optimal at the true model, m true. And if we perform inverse crime and assume noise-free data, then the observed is exactly f of m true. And therefore their difference vanishes. So the ideal p tilde optimal for FWIME is 0, or the null vector. And this was our initial claim at the beginning of this lecture series, where we said that we wanted the data correcting term to vanish when the true model is found. And here the inverse crime plus the absence of noise are very strong and inaccurate assumptions, but we just wanted to present the intuition behind our inversion scheme, and we are indeed adjusting our algorithm to address these issues. and we will soon post a video where we explain how we tackle this problem. So FWIME is going to be an algorithm that starts with p tilde optimal of mbad, updates the velocity model until p tilde optimal becomes 0. And here again, the main difference is that we're not looking for a perfectly focused migrated image, but we're looking for something that completely vanishes. Hence, we modify the conventional DSO penalty function by applying a strictly positive penalty value along the physical axis, in this example at the 0 horizontal subsurface offset axis. And now, our modified DSO function also penalizes points on the physical axis of p tilde op, as shown here by the pink dot. And now we illustrate the difference between the conventional and modified DSO operators by applying each one of them to the same common image gather shown here on the left panel. So here the right panel shows the result after applying the conventional DSO to the common image gather on the left. And this is the result after applying our modified DSO operator to the same common image gather. Notice the presence of energy even on the physical axis. And now I'm going to flip between the two panels in order to better compare. So this is conventional DSO, and notice that the physical axis is assigned a 0 penalty value. And this is our modified DSO. Conventional and modified. So in our modified approach, all the points on the physical axis are also assigned a non-zero penalty value. And this is indeed the operator that we will use in the annihilating term of our FWIME objective function. Okay, let's recap one more time all the information that we have acquired about our FWIME cost function so far. So the first term is the data fitting term and can be interpreted as a modified FWI objective function. And the second term, the annihilating term, can be now seen as more of a conventional WIMVA objective function with a slightly modified invertible DSO operator that offers a different way of measuring the unfocusing of p tilde optimal. The last piece of the puzzle is a trade-off parameter epsilon that balances the weights of the FWI and the MVA terms. And let's look at how the objective function behaves as we vary epsilon. And if we set it to 0, then the MVA term disappears. And we showed that the data correcting term p tilde optimal is able to perfectly match the misfit between the observed and the predicted data f of mi. And therefore, for any model mi, the FWIME objective function is null and constant, which is indeed not very useful. Moreover, for small values of epsilon, the second term dominates and FWIME is equivalent to performing conventional MVA. And finally, when epsilon becomes very large, we showed in a previous report in SCP-172 that FWIME becomes FWI. As we mentioned previously, the selection of the trade-off parameter epsilon is performed once at the beginning and is kept fixed throughout the inversion process. And though we do not have an automatic way of picking epsilon yet, we have gained some useful insight on how to select it. And if you're interested in knowing more about this step, please leave a comment and we will upload a video to describe our methodology. Okay, so now we understand everything about our objective function and we are done with the boring part. And in the last video, part 1, we're going to sample our objective function on a simple transmission experiment and we will show how it can convexify the conventional FWI objective function.